are the 4 ways you can configure an FPGA?
SPI, JTAG.
That JTAG is one,
Master.
now broad-based. Not, that's too much down in the weeds.
Using a microprocessor,
Through a microprocessor, so we have JTAG through a microprocessor.
using a Xilinx download cable.
No, not that, I'm gonna discuss it down a little more. You had the Xilinx PROM family, and then you had these VPI, SPI, memory chips. If you're going to use JTAG, and incidentally, as the Xilinx video pointed out, you should always provide a JTAG interface on any board that you build that has a FPGA on it. JTAG will directly program the FPGA. You don't have to have some non-volatile device. So during debug, that's incredibly useful because every time you make some modification to your code, you can download and reprogram the FPGA and run whatever test you want to, without having to program some non-volatile memory device and then download from that memory device into the FPGA. This slide right here illustrates the concept of daisy chaining. A lot of the FPGAs are JTAG compliant, and you'll only have one JTAG interface on the printed circuit board, but you can daisy chain the FPGAs if you have multiple FPGAs on the printed circuit board. And you can think of this as just one big giant shift register. So you program device number 3, then device number 2, then device number 1, all with a single download. So don't forget to do that. Now, somebody made the comment about a download cable. Your configuration information is on a file on the PC, and you're going to have to interface that to the printed circuit board using the JTAG interface. And this is done with a special type of cable. It's not just 4 wires. Remember, JTAG had TDI, TDO, T-clock, and TMS as the minimum. You can't just use 4 wires to bring it down. One of the reasons why is if you use a USB interface, I don't know how many of you know this, but USB is a 4-wire communications interface, but it's also differential, while the JTAG is single-ended. So you have a problem there. So there's a special type of cable that you use to interface your computer, your laptop or PC, to the printed circuit board. And these cables are referred to as download cables. Lattice happens to call them ISP download cables, but the term download cable is a cable specifically for a JTAG interface between a computer and a printed circuit. This is a little bit dated. This shows different configurations that you can have. The one used almost exclusively nowadays is the download cable has a USB interface, and you use a USB port to download your configuration information. This box here is actually a pod, and there is some circuitry in this, and we'll take a look at that in just a moment. In the days of the old ones, they used to put a 25-pin D connector, and that would plug into the printer port on a PC. Now, sometimes these cables on the printed circuit board end will have what is referred to as a flying lead connector. And so the individual wires have got a metal sleeve on the end. And you may have seen these, for example, if you used a logic analyzer. A lot of times the wires that you hook up to your circuit will have little metal sleeves. That's what you have here. So your JTAG connector on the printed circuit board is just 4 pins. And you just slide the leads onto the 4 pins to make a connection to the printed circuit board. Now, I mentioned that there was a pod. And this is the circuitry that's in the pod. You'll see there are some resistors and capacitors in here as termination networks. There are some buffers in there, a couple diodes, and so forth. You can make a JTAG cable if you want to, but they're relatively inexpensive. They only run typically $30, $40 or so for a JTAG cable, so many people don't do that. Besides that, it comes real nice, and the pod is all encased in some sort of lucite connector. So they're real professional cables, and they're not that expensive. But if you want to build your own, that's the circuitry that goes into the pod. Here are the connections that would go to, for example, printer port, and over here on the JTAG header, JTAG connector on the printed circuit board are your various JTAG signals. Now, as far as the configuration format itself, it turns out that these, it can be done in various forms. The .bit file is the one that is on the systems that you have over there in the circuits lab. And just to give you an idea of how big these configuration files are, this table shows for various Virtex devices the total number of configuration bits. And you'll notice that the minimum is 8 megabits. And it goes all the way up to almost an order of magnitude larger. So the amount of bits it requires to actually configure these FPGAs is quite large. However, we'll see with the BPI and the SPI interface, that is not a limitation. On D2L, I have put this particular application of indirect programming of BPI proms with the Virtex 5 FPGAs. What they mean by indirect programming here is through the JTAG interface, you are not directly programming the FPGA. Instead, you're programming a non-volatile memory device. And then the FPGA will get its information from the non-volatile memory device. So they come down here and it tells you a little bit about things that you already know. You have to be configured to power up from a non-volatile source, and it's traditionally accomplished with a JTAG interface, a microprocessor, the Xilinx proms, or as they discuss in this note, the BPI SPI. So I annotated the second sheet of this in red. BPI standing for byte peripheral interface. SPI, which is arguably more common, is the serial peripheral interface. The only real difference between them is on the byte peripheral interface, you're getting the configuration information a byte at a time, while on the SPI interface, you're getting it a bit at a time because it's serial data. So here's how this works. Here's a laptop, and it's running Impact, which is the download software that Xilinx provides. There's your download cable, there's the pod, and it's interfaced to the printed circuit board via a JTAG connector. There's your FPGA, and here's a BPI PROM, or it could be an SPI, serial peripheral interface chip. So here's how it works. Xilinx is going to provide a proprietary IP. What they mean by proprietary is you're not going to get the source code. If you will, it's kind of like executable code. So what the Impact does is it first downloads and programs the FPGA with this proprietary IP. What the IP does then is it converts the instructions into the command and control signals needed to program that memory chip. Now, we took a look last time at a table. There was, 19 JTAG instructions to program an FPGA. When those get downloaded, that proprietary IP generates all the necessary command and control signals, clocks, write enables, etc., needed to communicate with that memory chip to program it. That's why they call it indirect programming, because you're not programming the FPGA with the target application. You're programming that non-volatile memory chip, flash, PROM, what have you. After downloading the bit stream, the FPGA then automatically reads the flash memory to configure itself. Okay? So you download that proprietary IP. That allows now when the JTAG, through the JTAG interface, when your configuration information comes in, you directly program the memory chip. And then when that's all done, the FPGA resets and configures itself in the non-volatile memory. So this next, so that's kind of shown in this figure here, where this is your FPGA, this is your flash memory, and there's all the command and control signals. So essentially, the way this thing works in a little bit more detail is like this. You recall in the FPGA that is JTAG compliant, that all of the input and output pins have these boundary scan cells around them that effectively will isolate the pins from the internal logic. So through the JTAG interface, it's going to use these boundary cells, or boundary scan cells, to generate the necessary command and control signals for your SPI memory in this case. And this shows you in a little bit more detail what that proprietary IP actually does. It puts in a FIFO and then the interface driver for your SPI memory. The FIFO is so that you can download as fast as possible from the PC the configuration information, and then it can be sent with whatever timings required to the SPI memory. Down at the bottom, I thought this was a kind of interesting table I found. It gives you some of the timing required. If you're going to do a boundary scan type of interface like this one up here, that's the number of program steps, seconds it's gonna take to program the SPI memory chip. If you do the FPGA directly, it's 7, so that's a time difference of 190. That's why the simple designs that you did, how long did it take when you did the synthesis tutorial to download the code and see the FPGA operate? How long?
A minute or less.
A minute or less. That was a relatively simple design. It was just a binary counter and a driver for the 7-segment displays. Imagine a full-blown FPGA where you have to download 12 or 20 megabits of information. It can take several minutes to actually do the interface. So this is a typical SPI flash memory chip. It's only 8 pins. This would be a relatively small one. This would hold only a few megabits of information. You can get, of course, these a little bit bigger, but this is the smallest one. And it's only got 8 pins. So it's a relatively small chip. If it's in some surface mount package like small outline IC or something like that, it would fit on the tip of my finger. So you have 4 signals. That you have to worry about. The chip select, a clock, serial data in and serial data out. Obviously the serial data in is used when you're programming the chip, and the data out pin is where the configuration information will be sent to the FPGA. There are also 2 other command signals of interest. The hold, which allows the device to be paused without deselecting it, so that if you, for some reason, want to stop the download for a brief period of time, you don't have to restart all over again. And there's also a write protect input that you can prevent inadvertently writing to registers inside the chip or erasing the chip. I pulled this particular one here. This shows the protected memory addresses. This is an 8 megabit SPI serial flash, which is adequate to program the smallest of the Vertex 5 memory chips. And it shows how this is divided into blocks so that you can protect various blocks of memory. Then the interface itself is very simple. This is shown for the Xilinx 7 series FPGAs, as I put in this note up here. The Arctic 7 and the Spartan 7, Xilinx collectively calls the 7 series FPGAs. So these are all JTAG compliant, so they will have dedicated pins for your JTAG interface. There's your JTAG connector. There's the 4-wire interface to your SPI flash memory. So all it requires is 4 lines and a pull-up resistor. Let's see. Oh, right here are the mode pins. Remember we talked about mode pins, where those pins would be grounded or tied to VCC, so the FPGA will know where it's supposed to go to get its configuration information. So you see that it's a very simple interface, and so programming this flash memory is very straightforward. You can use the indirect programming method, download the proprietary IP, then start sending down the configuration information, program that. When it's done, this reads it out there. Question? Yeah.
So the FPGA talks over SPI to the flash device. I was just looking at all the IP blocks they had in the synthesis tool, and I didn't see a SPI thing, and I was wondering if there's a way to just hook into this existing SPI system, or if maybe they have one. 'Cause
There are some SPI memory chips. Not sure if it's SPI or the BPI, that you can program directly through JTAG.
Okay,
But for most of the simple ones, it's set up for indirect programming.
but I'm talking about like on the FPGA. If I'm on the FPGA and I want, like, I load from SPI Flash, but maybe I have some extra information in SPI Flash that I wanna access from the FPGA. Is there a way I can, say, hey, I wanna use that SPI stuff, that's built into the FPGA?
Yeah, you recall in the configuration video, they talked about two other related applications. One is in that non-volatile memory, you could have two different configurations for the same FPGA.
Yeah,
Or, if we go back and we look at this, where, let's say I've got 3 FPGAs to program, and I only have a single memory chip. That flash memory then would have the configuration information for all 3 of these.
yeah.
Okay, so the way that this would work, and let's see if I've got this here or, bring it over now. Oh, I didn't bring it. I guess
I'm thinking more like I wanna talk, I'm on the FPGA and I want my FPGA application to talk SPI. Can
Yeah.
I use that thing?
yes.
I can, okay.
Let me show it this way. This is something I'm covering in, here, that I've got this. Oh, no, hang on a minute. Scan testing figures. Sure if it's in there or not. I haven't got the information here, so I'll explain it this way. You can use these boundary scan cells to communicate directly with the memory. And you can have the FPGA, through these cells, generate all the command and control signals to that memory chip to extract any information out of that you want.
Okay.
So if the SPI is containing information that the FPGA would need in its particular application, through these boundary scan cells, it can communicate directly with that memory chip and extract the information while it's executing its normal application.
Do I have to write that whole SPI operation, or is there some kind of ID for it?
Well, there are a set of instructions that go along with JTAG, and I don't have the slides with me. There's
Okay.
3 mandatory instructions for JTAG. And one of those, the primary one would be external test. External test allows you to write to the boundary scan cells to drive the command and control signals to the SPI memory chip.
Okay,
And so it would be through those instructions that you would access it if you were gonna use the SPI for something other than just configuration.
yeah, okay,
So it can be done.
thanks.
Okay. Now, before we look at the synthesizer user's guide, let me give you a little bit more specific information about the logic synthesis process. So this shows a VHDL description. It could be Verilog just as easily. And from that hardware description language, I would get a circuit netlist. This schematic that you see here which is shown in more detail here, that VHDL description was for this particular circuit. So you see you've got some exclusive NOR gates and some NOR gates and NAND gates and OR gates and so forth, and a couple registers. So that would be the circuit at the gate level that you would be synthesizing. Okay. Now the synthesis process can be broken down into 3 general processes: mapping, placement, and routing. So what I want to do is I want to take this circuit and do mapping, placement, and routing in an FPGA. In the first phase, the mapping phase, what I'm going to do is assign all of those components to virtual LUTs and registers. Now this is just a arbitrary mapping, and I'm not making any claim that this is particularly efficient. But you see that these 2 gates are going to go to virtual LUT 0. These gates go to virtual LUT 3. Since these are virtual LUTs, the numbering really doesn't matter. I mean, I could have called this 0, 1, 2, 3, 4, 5 if I wanted to, because these are just arbitrary labelings. But what I have done is map gates to LUTs, virtual LUTs. Similarly, the registers I can map to virtual registers. FF1, flip-flop 1, FF2, flip-flop 2. The next phase is the placement phase. And in the placement phase, what you do is you physically assign the virtual LUTs and registers to physical LUTs and registers in the FPGA fabric. So LUT 0 got put into that configurable logic block, as did LUT number, was that 2? These 2 flip-flops both got put into that configurable logic block, and so on. So in the placing or placement phase, the virtual LUTs and registers are assigned to physical LUTs and registers in the FPGA fabric. And then the last phase, the routing phase, once I've got a physical placement, now I can determine how to route between individual configurable logic blocks to hook everything together. So if you go from a hardware description to a gate level event list, you then go through the mapping, the placement, and the routing, and everything gets put into here. Now, as we are going to see when we go through the synthesizer user's guide, there are options that you use during the synthesis process that will affect the placement, and of course that will have an impact on the routing. Okay, but those are the three phases. Now, with that in context, what about black box synthesis? If you go to the mapping phase, your circuit has been partitioned into virtual LUTs and registers. But for black box synthesis, as you recall, you don't have a functional description. You therefore don't have any gates. You therefore can't assign them to virtual LUTs, and so that procedure that we just went through doesn't seem to apply. So the question is, how would this change if I have to do black box synthesis? Now, you recall that you have to do the black box synthesis when?
When you don't have a net list from the IP provider.
Okay, when I'm using some sort of generation tool to use a FPGA vendor, second party IP, or a third party IP vendor, third party IP, I'm using one of their cores. So you recall that the IP vendors, whether they're second or third party, provide three types of files. What's one file? What are they?
.b file.
No, tell me the type, what are the files, not what their extension is.
The
Behavioral wrapper. What's another one?
hard macro.
The what?
A hard macro file.
Hard macro file. And what's the third one? Everybody forgets the third one. An ASCII file that will show you for Verilog or VHDL what syntax you should use to instantiate that core that you've created. Yeah,
You left the T on syntax.
thank you. Okay. So, I'll I'll have my Verilog files. And I'll add to that the behavioral wrapper. And I can go into a simulator. So I can functionally check out the design with that core that I've created. But this behavioral wrapper is not synthesizable. So when we get to synthesis, I'm going to remove the wrapper and instead put in the black box. And now I can go into the synthesizer. And out of the synthesizer, I will get the net list. Now, you recall from the previous lecture that what this black box does is it creates a placeholder in that net list. So when you go back to the placement, there will be a hole, if you will, but a defined place that the place and route tool will need to assign to physical resources in the FPGA fabric. But instead of using virtual LUTs and registers, it will use that third file, that hard IP, hard macro IP, that is the net list for the core you created. So it's going to use the virtual LUTs and registers in the placement phase and any hard IP macros that you used when you created your design, and then it gets placed. Now your black box does define the I/O ports. So when you get to the routing phase, that information will already have been provided. Because the hard IP macro that gives you the net list for the core you created only tells you enough information to support physical placement. It doesn't tell you anything about routing. The black box that you created, that defines the routing. So that's how the cores would fit into this three-phase synthesis process. I'm going to spend some time going through the user's guide for simplicity. And I can't stress enough that if you're going to do FPGA design, you're going to have to spend time, a lot of time, going through the user's guide for the synthesizer that you're going to use. This document, I think, is 690 pages. And there's an awful lot of information in there. And so I've got selected pages that I'm going to go through. This entire document is on D2L. But what will be appearing in the lecture notes are only the pages I want to focus in on. Now, the pages that I'm selecting to go through are just to highlight certain features so that you get some idea of what this synthesis tool is capable of doing and some of the options and features that you have. And of course, if you're going to use some other type of synthesizer other than Simplicity, there will be a corresponding user's guide for it as well. Incidentally, I had made the comment about Synopsys, who's out there off of Cornelius Pass Road. Several years ago, they bought Simplicity. And so the Simplify family of synthesizers is now under control of Synopsys. Okay, so first, let's take a look at the table of contents to show you the type of information you're going to get. In the introduction section, they're going to talk a little bit about the FPGA design flow. And then this, as you're aware, since you went through the synthesis already, that you're going to have to set up the project for your synthesis. There are a number of constraints, attributes, and options that you can set in the synthesis process. This is something that we haven't talked a whole lot about, but we will now. Result analysis. There's going to be a series of reports that tells you exactly what got produced and how your FPGA is going to be programmed, so that you can see whether or not you met your constraints. One of the most notable ones, which we will be spending most of the rest of the course on, will be the timing. Not all, but most. And you can do stuff like explore your design hierarchy. You can find different objects. There's hardware description language, analyst tools, and so forth. There's a physical analyst, which is going to show you how things actually got placed inside the FPGA. So you can get some idea of what configurable logic blocks were used, which I/O pads were used, and so forth. There's a whole series of sections dealing with design optimization. And we'll take a look at some of those. For finite state machines, inferring ramps, retiming, so forth. There are some design planning and optimizations, pin assignments, and so forth. Vendor-specific optimizations. Synopsys is a general, the Simplify synthesizer is general. In other words, it's not just tied to Xilinx. It'll work with other FPGA vendors as well. So they have some sections in here where they're talking about working with Altera designs, with Actel designs, and so forth.
Do you recommend that we use this guide rather than
That's the kind of question like, what C compiler do you want to use?
Yeah.
It's just,
Doesn't matter that much.
and if you want to use some other one, let's say from Leonardo Spectrum, or one of the ones from Mentor Graphics or something like that, you're going to find similar type of information. They all work with different types of families, and their user's guide is gonna have the same type of information. Design planning for vendors, I'm not gonna spend much time on that. And I will spend, just a brief amount of time on design flows. This is page 1-2. It says simplify and simplify Pro or logic synthesis tools for FPGAs, complex programmable logic devices. The software uses high-level descriptions written in Verilog and VHDL. And they have proprietary behavioral extracting synthesis technology that converts it into high-performance design netlist. Editorial comment: you will still find current textbooks written for like 171 and 172 where they have hardware description languages in there, and they still are publishing books that use Able. I'm not sure how you get Able converted into netlist to programmable logic devices. Verilog and VHDL is really all you need. Simplicity FPGA tool features, they give you a table that shows for the 4 different versions: the basic version, the Pro version, the Premier version, and the Premier version with Design Planner. And it shows the capabilities. I thought this was interesting. The basic version doesn't support CoreJet.
You have to make everything yourself.
So you have to make everything
It's
yourself.
gonna take you forever.
Yeah, so probably don't want to use the basic. In fact, there's a lot of X's missing out of here. First of all, no timing analyzer.
You're never gonna get anything done.
Yeah, you're not. There's no finite state machine viewer, so it's pretty limited. So here on page 1-9 is the process that you will go through. The HDL design entry, logic optimization, technology mapping to a particular FPGA component. Then you go through the P&R, and then finally you get your configuration file that you can download. And in this, it says they only support Verilog and VHDL. In this and then they talk about each one of these blocks in the logic optimization. One of the things that you do here is restructures the original network into a set of combinational functions. They're represented as a Boolean network. At this point in the design, you modify the initial design to optimize area or speed of the final circuit or both. So, but we'll take a look at some of this in more detail. Page 1-12 talks about starting the software. And if you're on a using a command line interface, That's all you have to type in depending on which version that you're using. And that starts the synthesis tool and opens your project window so that you can start to put together your project. So this is the Simplified Pro, and you're using, you've seen this when you went through the synthesis, the project window that you got for that particular synthesizer. And these are all pretty much standard.
That TCL stuff, I saw that in the user manual for the other one. Is that like everything has TCL? What is that?
I'm not sure why they still have TTL.
Yeah.
I don't see what the applicability of that is for FPGAs. So here is your, the steps that you're gonna go through for the logic synthesis. After you create your project, you're gonna add the source files. You're gonna set any constraints that you may have. I think the only constraint that you set when you did the synthesis was the pinout. I don't think you did anything else. Then there's options for finite state machine encoding and so forth, run your software, and then analyze the results. Now you didn't analyze the results, you just had a FPGA running that was sending data out periodically to a 7-segment display. We're going to look at some of the results that you get from the synthesis process. So the first thing that you're going to do is the project setup, where you're going to specify your source files for hardware description language, any processing files, and so forth. And this is all GUI based. And it just takes you through on selecting files and OK, and a lot of this stuff you went through. One of the nice things is that these synthesizers do have a built-in text editor so that you can modify your HDL code. And the thing that I like about these, unlike a lot of editors if you're using an external editor, is that they color code different things for you. You'll notice that in this particular case, the keywords are all in blue font. And things like, this is a synthesis attribute, and it's in green font. So it makes it a little bit easier to find things in your file if you use their built-in text editor. You do, however, have the option of using any external editor. And they mention a couple here for Unix, VI or Emacs, if you happen to be familiar with those. So you can use those as well. And there is a window where you will choose whether you want to use the internal editor or the external editor, and then you will give the appropriate commands so that when you go to an edit function, it will call this particular editor. In this case, it's going to call the VI editor.
It should never be Emacs.
Yeah, I know. I still use VI quite a bit if I'm just doing ASCII editing, ASCII file editing. I haven't used Emacs in eternity. So then you set up your project files. So you create the project file, or you can open an existing one, make any changes, define which files you want to use, and so forth. And so you have a GUI where you can start to select the files that you want to add as you start building up the project. And you have to specify the type of file. Making changes to the project, of course you can add, delete, or replace files. This talks about replacing a file in a project, and it takes you through the steps that you have to do. The thing that's nice is you don't have to, if I've made a modification to one of my Verilog files, I do not have to start over at the beginning. It's a shortened process to replace a file in a project. Yeah.
How does it know which is your top level module?
Usually that's something that you have to specify. That'll be one of the entries that you put in. You'll click on one of the files and then put in, this is my top level file. This is something that I wanted to point out specifically with these synthesizers and specifically with this one, and another one why you don't want to use the basic simplify tool. As I said, there's not much you can do with it. Mixed language. Some of your modules could be written in VHDL. Some could be written in Verilog. Some could be written in System Verilog. It doesn't matter. You can mix and match different hardware description languages in this. But I thought this was interesting. It says with the Simplified Pro and Premiere, you can use a mixture of VHDL and Verilog designs. You cannot use Verilog and VHDL files together in the basic Simplify tool. It's got to be all VHDL or all Verilog. Maybe that basic tool is the student edition. Something like that. Okay, let's take a 10-minute break.
Have you ever gotten any IP or core IP modules from opencores.org? No? Okay. I was looking around and I saw this bunch of basically just open hardware stuff people writing.
The problem with that stuff is, if you go to a third-party IP vendor, they work with the FPGA vendors to make sure that their designs can be easily put in and they're efficient implementation. If it's an open source sort of thing, who knows what it was tested against?
Yeah.
It could have been, they just picked some vanilla FPGA, yeah, well, it was synthesized.
Yeah.
But it may not be synthesized very efficiently.
It does look like what they said on there, and most of them are really old and stuff. But it had like an iceberg C controller and stuff. So I was like, hey, that's kind of nice because I couldn't find some of them in the Xilinx cores.
Really?
Yeah, there was no iceberg C, just iceberg S, which I thought was weird.
They didn't have I2C.
Or Spy, which I also thought was weird. But
Uh,
maybe I couldn't find it. I don't know. I looked in all the folders, so I don't know.
Well, let me see if I can find something.
Because I was thinking it's, there's got to be some. I think they might have had UART in there by default, but. Yeah, but this stuff came up and I saw this and then it wouldn't let me actually like see things from them, so I wasn't sure if these are things I might have to pay for or something.
Oh, you notice? Vendor.
Yeah,
It's third party.
okay, so they pretty much assume you're.
Yeah,
gonna
they're
buy
on
it.
the circuit. Oh, okay, so these are third party IP.
So they don't have any ones that they built.
No. To be honest, most of what the FPGA vendors are going to give you are the really basic stuff.
Yeah,
Binary counters.
yeah, that's what it looks like.
That's commonly used logic that sign and just save you some time, but once you start getting up to, bus controllers and things along that line, it's a little more sophisticated.
Yeah, it just
And
seems like
so-
you need to do I/O, so I thought that would be kind of like a basic thing to have some of these I/O.
Yeah,
monitors.
apparently it's not that basic.
Yeah.
So that's where the niche is for the third-party IP vendors.
Okay, so that's what they did in there. Yeah, I saw there was like Ethernet and stuff by default, and I was like, why are they doing like, 1 gigabit Ethernet when they don't have I2C? It's like, I feel like I2C is something you'd want sooner than Ethernet. Anyway, what do I know? Yeah, looks like there's another third party here.
No, Xilinx does produce one.
Okay.
Xilinx gives a SPI interface. Here's the data sheet for it. Vertex 5.
That's the one we have in the lab, the Vertex 5?
No.
Okay.
That's all I got.
I think that's
It's that
a
simple, it's that simple.
Vertex.
Okay.
Xilinx processor.
Yeah.
FPGA. But I think it's Artix.
Artex.
This shows the Vertex 5, how many LEDs and registers are used to the SPI interface.
Cause like I talked to you the other day, I wanna try to see if I can implement the neural network. And, there's all sorts of stuff, but I figured I could kinda simplify it by doing things like, instead of using floating point numbers, just do the math beforehand and do a big lookup table or something like that. And then I can, kinda do
Well,
some
you
things like
can
that.
do integer math.
Yeah, cause then I can do integer math, but the problem is, some of the things are like, it wants you to take E and then take E to the power of negative something, and then that's floating point,
Yeah.
stuff, and it's like, that's like one of the key operations, and so, yeah.
But it
I wanna
depends on
mess
what
with
kind
it.
of FPGA that you're using, because, like the Vertex 5, for example, has got the DSP slices,
Yeah,
and those might give you support for real numbers.
okay.
So, I don't know what FPGA you're in.
Yeah, I don't know.
If you
it's
use
just
those
poking
demo
around.
boards that we have in there, there's no reason why you couldn't.
Yeah,
You need to find out what that FPGA is on there. It's an Vertex, I believe, but I'm not sure about the exact number. Pull the data sheet and then look at the, I think all of these now have DSP slices.
yeah,
Find out what the capabilities of that DSP slice is, and if it supports floating point math.
okay, and that'll be pretty much just as fast
Yeah.
then?
But then you're gonna have to write your code to infer that when you do
Yeah.
that mathematics, it's put into the DSP slice.
Yeah, that's the thing is I don't totally know how it would work right now, but I wanna play with it, and of course, the first thing I was thinking was, I need to get things in and out, so.
Yeah, I'm
it's,
not sure. You're gonna use I2C, what do you communicate?
well, I was just gonna have, my approach was gonna be a microcontroller, and then that microcontroller would be attached to the FPGA and as well as like a camera or some kind of audio recording device, and then, take a picture from the camera and try to feed it through the neural network on the FPGA, grab the output, and, use the microcontroller to display it. I guess you could do it all on the FPGA, but I just am not super familiar with it. And my understanding is that,
We didn't discuss it. In chapter 3. They do describe in there how you can represent real numbers.
okay, That's interesting.
Adding and stuff, I'm not sure.
Yeah. Because I looked at all the operators to make sure I could do everything, and I was very surprised when they were like, oh yeah, you know, the power is a default electrical operator. That's very good for me, because even in some programs, like C, that's not a default thing, right?
So, I think all the arithmetic operators should be, you can get some detail. I think it was chapter 3 where we started to talk about that, the chapter where we introduced the tick mark B representation.
Yeah.
It's in that chapter. There is a section on building.
Yeah, that would be interesting. That would make
So Verilog will support it.
Yeah, I think once I figure out how to do that, I pretty much know generally how to structure it, and then I just need to figure out how to get things in and out. What do you do when you do your FPGA stuff? Do you?
Most of the designs I've worked on were everything was in the FPGA.
I do not.
Interface and external processing.
Yeah, there's no, it doesn't do it all.
But we're going to, give a chance to speak microwave, microcontroller for sure.
I saw that as
Microwave processors. And so you can build up a small processor for microcontrollers on the, totally on the FPGA. So you may be able to get Okay, so this is page 3-2, setting device options. These are global options you want to set for the synthesis run. These include things like part selection, part speed, grade, etc. As I'm sure you're aware, if you specify a particular FPGA, it is typically available in a variety of different speeds and so forth. And so that's some of the options that you have to choose when you pick a particular FPGA. Let's see. So for example, in this case, this is a particular Xilinx Vertex 4 FPGA selected. There's the speed, there's the package, and so on. And this is all GUI interface, so like it says, you can type in a value or check a box. On page 3-4, this is the first reference I'm aware of. To set device options with a script, you use the set option tickle command. TCL, tool command language, is a widely used script file for FPGA synthesis. I'll be discussing a little bit more about this later on in this user's guide. But these are different things that you can set for options for the device that will drive the synthesis. You can set fan out, maximum fan out, the package type, the part number, any area constraints that you might have, so you can set all of those. There are also some optimization options that are available dealing with physical synthesis, finite state machine, pipelining, retiming, and so forth. Specifying global frequency and constraint files. When we get to the timing constraint video, one of the things that the speaker will make very clear is the notion on timing. If you don't provide any timing constraints, the synthesizer assumes you don't care about timing. And that's fine. Then your design is going to be put in there without any consideration of timing, and you may find it won't work at the clock speed that your specification dictates you must be able to do it. So in a simplifying, it's a simple way of determining what clock frequency you want and any implementation options, etc. And you can specify a constraint file if you've collected all of those constraints into particular files. Setting the Verilog and VHDL options, the one thing I wanted to point out here is on this one, and this document is from 2005, your choices are for Verilog, Verilog 2001 or System Verilog. Verilog 2001 is the standard that your Palatnikar book was based on. There have been a couple of revisions to that standard since then, but the changes have been very minor. They upgraded some things dealing with modeling transistors and things along that line. Something called a scope window, which you can set some of the constraints, and these are some of the constraints that you can specify. You can define clock and path constraints, multi-cycle paths. Some paths that you have for data to flow through your design have clocks operating at different frequencies. Those are what is referred to as a multi-cycle path. You can specify I/O pad types, gated clocks, and so forth. Let's see. Defining false paths. A false path is a path that data flows, but you do not want to have the timing analyzer analyze that particular path. Maybe you're only interested in one or two critical paths and not the other ones. So you can identify data paths as being false paths so that they're not involved in the timing analysis. On page 360, they talk about working with constraint files. These are ASCII text files. They're generated by the scope interface, or you could write your own TICL code to specify the constraints that you want. Now it says, you can add constraints in constraint files, or you could put it in the source code. And I will be showing you an example later on where we used a constraint described in the source code as a synthesis attribute. So you could specify some of your constraints that way. However, it says it's better to use constraint files. That will make your source code more portable. Code reuse is a big thing with these hardware description languages. So we made the comment before that instantiation limits, it gives you more control, but it limits portability. So does overuse of system attributes or synthesis attributes in your source code. It limits portability. So if you have constraints, it might be preferable to do this in a constraint file rather than in your Verilog code. Chapter 4 talks about results analysis. It's going to talk about the log, handling messages, errors and warnings and so on, timing reports, and so forth. There is a running log, which I'm sure you were aware of when you did your synthesis, that would tell you how the synthesis is progressing, and it would identify any errors or warnings or what have you. You can have this just put into a log file, but what you may find is a lot more useful is this log watch window, which on the synthesizer you used was down at the bottom, and it would scroll up and start printing stuff out rather than put it into a separate file. Warnings and errors. Now they color code this in that log window, and here it's telling you what colors they're using. Notes are just going to be in blue text. Warnings or errors are in purple or red, so they really stand out when you are scrolling through, because that log window can get very, very long for a very complex FPGA synthesis. So having this color coding is worthwhile. Resolve any errors and check all warnings. You have to fix the errors because you can't synthesize a design that has errors. Warnings can be ignored. Give me an example of a warning.
The two types of datas are not the same, like we're trying to put an unsigned integer to an integer or something. Of course, that's more general programming.
Looking for one particular example that we discussed quite extensively before.
Oh, the inference.
Latch inference. If you don't write your code correctly, you're going to infer a latch. That generates a warning, not an error. You can implement a circuit with a latch in there if that's what you wanted, but that would be an example of a warning that you get. And you can choose to ignore that if you wish. But all errors you have to fix or the synthesis won't complete. So specifically with handling warnings, it says if you get warnings after a synthesis run, you need to do the following. First thing is read it and decide if something, you need to do something to add or whether to ignore it. It does have the capability to give you a little more information rather than just some cryptic statement. Warning, blah, 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 and you may not understand what that means. There is kind of like a help window that can pop up to give you more information.
One of the synthesis ones, when we had to do that one, I went through and I tried to synthesize, or I tried to simulate, and it just said error in module, and that was all it said.
Yeah.
And it's like, that's as unhelpful as it gets.
I I have not for a long, long time been in favor of Microsoft products. And many years ago, I was doing a lot of C programming. And the Microsoft C, I dumped that as quick as I could. They would produce the most cryptic warnings. You're writing just basic code to do something like multiply two matrices, and you get this nebulous number, and it would say, exception handling error, blah, 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 and where am I supposed to go to get information on what the heck that means? So I went to some of the secret. Basic operations in the schematic views. The RTL and technology views are schematic views used to graphically analyze your design. So you can get some idea of the type of circuit that actually got synthesized. As opposed to, yeah, we use these LUTs and we use these registers. Okay, so what did you do in those LUTs and registers? So we'll give you kind of a schematic representation of what actually is going to be synthesized. So it talks about how you can open the views, and it talks about differentiating the views between an RTL view and a technology view. And they show an example here. This is an RTL view. It's not quite a block diagram, but it gives you kind of an overview of what type of circuitry got synthesized. Or you could go down to the technology view and get far greater detail. So you get some idea of what actually is going to be synthesized. You can explore the design hierarchy. Remember, one of the things when we talked about handling complexity was the first thing was to partition your design, which creates your design hierarchy. It says schematics generally have a certain amount of design hierarchy. You can move between hierarchical levels using a hierarchical browser that they provide. And they will provide a list, and you can click on the appropriate plus sign to expand out to see which levels of the hierarchy are below this level in the design, this level in the design, and so forth. Analyzing timing. You can analyze clock trees in the RTL view. What's a clock tree?
You have your real-time clock or your clock source, and then you route it on your PCB, or I guess in this case on the FPGA, so sometimes
Yeah.
it's farther away.
It's the special trace
Yeah.
associated with clock signals. And it shows you how your clock signal is routed through the FPGA fabric to get to the individual designs. You do have to spend some time on the clock tree because you need to make sure that things are balanced properly. If they're not balanced in terms of circuit routing length, you can run into clock skew problems.
Like, when would you see that though? Like, how would you know you're gonna run into that problem if it's, millimeters or something?
No, what you do is you just look at it from a high-level view. If I've got a bunch of circuitry and the clock is routed, that's fine. But now I've got over here in the configurable logic block, and I've got that same clock is routed out to that cluster out there, I've got some problems with placement.
Okay.
Critical paths. Those are your paths that have the most significant amount of propagation delay in the processing of the data. You do spend a lot of time on the critical paths. When we look at the video on global timing constraints, it will talk about that, those critical paths. You can actually identify the critical paths, and this HDL analysis tool makes it simple to find and examine the critical paths in your code. So you can identify which are the critical paths and just restrict your analysis to them. Okay, so it takes you through these, this is in chapter 4, it takes you through how you can identify the paths and what you click on in the GUI and so forth. Viewing the results. This is an example of a report that you're going to get. And they show this example for this particular path. It shows you which module it came from and what the net name was in that particular module. Tells you if it was going to a LUT or whatever. Tells you the propagation delay, tells you the fan out. So it gives you a lot of information associated with timing. There also is a physical analysis tool when you get to the placement phase and you're now assigning those virtual LUTs and registers to physical configurable logic blocks. This will give you some indication of how things were placed inside the FPGA. That may affect some of your constraints because you have to move stuff around to ensure that you can meet some timing constraints. I will define a term here. It says a physical analyst provides a visual display of the placement and global routing of the design after running place and route with back annotation. In back annotation, what you do is you can extract from the FPGA the configuration information and resimulate if you want to. With a physical analyst, you can also view those critical paths. And here's an example of what some of that may look like. Next thing is design optimization. Here are different things that you can optimize. Notice a lot of these deal with finite state machines. I'm finding black boxes for synthesis. Pipelining, retiming, inferring RAMs, inferring shift registers, working with gated clocks. So they give you some general optimization tips for your source code, and these are the types of things that you would find in that HDL coding guidelines document that we talked about. They talk about removing any unnecessary priority structures and timing critical designs, And one of the classic examples of that is to use a case statement instead of nested if-then-else statements. If your design includes safe state machines, use the synthesis coding attribute with the value of safe. We're going to discuss that one a little bit later. Make sure source code supports inferencing or instantiation by using architectural specific resources like memory blocks. Area optimization. Increase the fan-out limit when you set the implementation options. If I restrict the fan-out, how do you think that would affect area?
It's gonna need to it's gonna need to use more things so it can fan out to like 2, and then those 2 can fan out to 8 each or something.
No. Let's suppose I set my fan-out limit to 50. And in a particular design, it turns out that the fan-out limit, or the fan-out turned out to be 60. How could I reduce the fan-out? And it's more than just adding a buffer. And, half the inputs are driven off of one buffer and the other half on another. The classic way of reducing fan-out is to duplicate the circuitry. That affects area usage. So for example, if I have a circuit that's generating a initialization signal and the fan-out is very large, and let's say that that initialization signal is INIT, I-N-I-T. I could take that circuitry and duplicate it, call the outputs init1 and init2. Some of the circuitry would be driven off of init1, some would be driven off of init2. The modules are identical, so they're going to behave the same way. And that's the classic way of reducing the fan-out. Or I could cheat and go into my synthesizer and increase the fan-out limit to say 70 or 80, then I don't get an error. Resource sharing we talked a little bit about. For large finite state machines, they say use gray or sequential encoding styles. Timing optimization settings. Use realistic design constraints, about 10 to 15% of the real goal. Over-constraining your design can be counterproductive because you can get poor implementations. Talk about balancing fan-out. This is interesting. Try disabling resource sharing if your critical path goes through arithmetic components. For finite state machines, use the one-hot encoding style because it's often the fastest implementation. For design of black boxes, characterize the timing models accurately using, and they give you 3 synthesis directives. We didn't talk about that. There are these synthesis directives that you can put in a synthesis black box so that timing analysis can be conducted on that particular core, even though it hasn't been actually synthesized. Because the synthesizer is just going to get a port list, but these directives you can put in there that says, when you do your timing analysis, this is what you use for things like propagation delay, setup time, and so forth. talks about sharing resources and some things you can do. Setting fan out limits. Controlling hierarchy flattening. And they do that with the synthesis attribute. I need to explain design flattening. Here's a simple design, but I think this will get the point across. So I've got a modulo n counter, and this is going to be partitioned into two modules. I have one module that's a binary counter, another module that's a decoder, and when the appropriate number appears on the binary counter output, the decoder will assert the clear to truncate the count sequence. Standard modulo n counter. So that has those two modules underneath it at the next level. So here's my design hierarchy that I'm using. So there's my modulo n counter. There's the two modules underneath it, a binary counter and a decoder as shown in that block. And then the binary counter, I go down another level, I've got some flip-flops and some glue logic in there. And so that's the complete design hierarchy for my modulo n counter. Design flattening removes the hierarchy by merging modules, and when you merge modules, you remove the hierarchy. So what I've done here is I've taken these, which were in separate modules, and merged them all in and coded them up in this binary counter module. Now, here's the effect. Design flattening makes it easier to optimize the circuitry, but the larger modules are less portable and reusable. These synthesizers have a problem trying to optimize your design across levels of the hierarchy. Here, if I tried to optimize this portion, the synthesizer would have to work at the third level and the second level of the hierarchy. If I use design flattening, I only have two levels in the hierarchy, and it's easier for those optimization tools that are part of the synthesizer to work.
What, I don't understand why it would be less portable, because this happens during synthesis, so aren't we already locked in to what we want to do?
Well, what they're talking about here is if you invoke some of those optimization features.
Yeah.
If you have flattened your design and defined the hierarchy this way, it'll have an easier time of meeting those optimization
So
techniques.
we're the one who flattens the
Correct.
design. Okay.
Yeah, you flatten the design.
Okay, I thought it was like automatic.
Well, what this says here is you can control the level. You can let the synthesizer do this and say, okay, I'm going to flatten it to do the optimization.
Okay.
You can remove certain levels. You can flatten the current level if needed for optimization. So this is just a temporary thing. It's not modifying your code in any way.
So it's
But-
like an inline in C or something like that?
Yes,
Okay.
yeah.
So, if that will make your, make it easier to meet different requirements, then what is the downside of letting it flatten your design? I mean, why would you not just say flatten all my designs always?
Well, taken to an extreme, you have one level in the hierarchy.
Yeah.
The thing is, how much do you want to actually flatten your design? In this simple design here, flattening, this was just for illustration purposes. This probably is not going to make that much of a difference.
Yeah.
If I flatten this right here, the binary counter and the associated decoder would all be in that one module. That's a lot easier to design because I don't have any interface signals between them. So all I'm saying here is if you're required to optimize and you have to work across multiple boundaries, it becomes more difficult to do the optimization than if everything's in one module. That was the only point of the design flattening. But it does say, design flattening makes it easier to optimize the circuitry, but the larger the module becomes, the more you may run into problems with portability. For example, if I merge those two, those are probably going to be instantiated, not necessarily inferred. More instantiation, less portability. There is attributes and directives you can have for finite state machines. They show in here, and this is a rather important table. It's on page 616. If area is important, use sequential encoding in your finite state machines. Speed, use 1 hot. Recovery from an invalid state, if that's important. If your finite state machine can get into an invalid state, not sure how that would happen. You should use the synthesis attribute of safe, and what it does is it forces the state machine to go into a reset. And incidentally, you can combine those like it shows here. Synthesis encoding, safe, and 1 hot. There's also a thing known as a symbolic finite state machine encoder, which automatically recognizes state machines in the design and optimizes them. They talk about pipelining and design. It's only available, it's not available on the basic simplify. What's retiming? Great exam question. What is retiming a design? I knew that would get attention when I said that's a great test question. Remember the RTO model, you have register, block of logic, register, block of logic, register, block of logic, and so on. In retiming, what you do is you take portions of the code and you move it on the other side of a register and incorporate it into another block between a pair of registers. So you're retiming the circuitry. And what that tends to do is, remember in that RTL model, the propagation delay through that combination logic block is going to ultimately determine your clock frequency. When I do retiming, it turns out that I can actually reduce the clock period and wind up getting faster clock. Yeah.
So we talked about always registering outputs, but is there, I mean, I would assume most of the time you'd have more than one gate, right? So you'd have like
Oh,
several
yeah.
things, but
Yeah.
is there ever a time where you're like, okay, this is ridiculous, like I've got, you know, I've got like 30 gates before a register, and how do you know that's gonna happen? Like, how do you see that?
That's where the timing analysis comes in.
Okay.
Because you'll have a critical path, and it's gonna define for you what the propagation delay is along the path. So you can see, gee, this block, I can't meet a timing constraint. And we're gonna see an example of that in a future lecture where it can't meet the timing constraint. The only way to do that is to retime the circuit, which means I'm taking logic from one module and moving it over to a different module. Which is actually shown in this example here. Where I've got some registers and a couple of LUTs that are in series, and see how it's been retimed. One of the LUTs moved to the other side of the registers. Talk about inferring ramps and ways of doing that. Page 676, they talk about mapping ROM to block RAM. And it tells you that you need to put a D flip-flop register in front of the ROM and so on to be able to do that.
Is that an actual type? Like you instantiate the D flip-flop or something?
Yeah. This is where, I'll finish this up on Thursday, because I do want to spend some time on the gated clocks. Okay. Everybody get their homework. Where would you find that information out?
Yeah.